Dear friends, welcome to this electrical engineering knowledge sharing channel, AMP Power System. We are going to discuss today a new session, that is session 7 under workshop 5. In this session, we are going to discuss about the cable sizing, power cable sizing. We have already discussed generator sizing, transformer sizing, switchgear sizing. Now we are going to discuss the nervous system of the various equipment by which various equipments are interconnected, that is a cables. So this cable sizing is one of the important electrical activities in the design and digital engineering. So we are trying to cover this cable sizing calculation in this session. So let's start this session. Now, before going into discussion on this cable sizing, we should have a preliminary discussion about the construction of the cable. What are the various parts of the cable, and for the various parts, which parts are important for deciding the sizing, or in deciding the sizing, which part we need to address when we are considering the system design. We are not going to discuss the sizing of the cable from the construction point of view. We are going to discuss the size from the application point of view. We have to use the cable in a system. So we are going to discuss how that system design asks for cable sizing. So from that point of view, we will be discussing the cable sizing. Now when you look into the cable, what this cable is doing? Cable is carrying power or current from one point to other point, or it is transmitting or distributing power from one point to other point. So when the current is being carried by some device, that device must have a conductor, that is which will conduct the current. So we know generally there are two types of conductor we use. One is aluminum conductor and another is a copper conductor. So these are two mainly material we use for the various conducting purpose, electricity conducting purpose. This will be one of the integral part of the cable. So when we want to carry the current from one point to other point through a device, this device must have a conductor. That conductor will carry current, and in your daily use, you use either aluminum or copper. That is one part. Second part, this conductor need to carry current, but all conductor or all size of conductor cannot carry all size of current. So for each size of conductor, there is a current carrying capacity. So that is our purpose over here. For carrying a certain amount of power, what is the size of the conductor is required. That is from the system engineering point of view, that is we have to decide. That is the first part. So in deciding the cable sizing means first we have to decide what size of cable or what size of conductor is required to carry a certain amount of power from one point to other point. Second point is this conductor, suppose this is a conductor, I am drawing the cross section area, suppose this is the conductor which is carrying the current. Now this conductor, it is when you apply a voltage source, suppose there is a voltage source over here which is connected to this conductor. So immediately this conductor will be subjected to this voltage. If it is 6.6 kV, this conductor will be subject to the 6.6 kV voltage. Now this conductor, when you carrying current from one point to other point, we cannot keep the conductor open. So in that case, when anybody come in contact with the conductor, immediately he will be subjected to 6.6 kV voltage. That it is a huge health issue. It is a safety. You cannot use this way. You cannot keep it open. That means we have to cover this conductor with some material on which surface voltage will be zero. So if anybody touch on this cable, nothing will happen. There is no damage or there is a life accident will not be there. So that means there is some insulating material is to be covered by the over the conductor, so the conductor voltage will not come to the surface of the cable or surface of the device. So that means this conductor will be wrapped with a insulating material which will this 6.6 kV voltage will not come to the surface. The surface voltage will be zero. We have to decide the insulation thickness in such a way so that the 6.6 kV voltage will be diminished over this thickness. So at this point there will be no voltage. So this part, that means there will be a conductor shall be wrapped with some insulating material to avoid the voltage on the surface. So the second thing is requirement insulation system. Third, this insulation system, if it deteriorates with the time, suppose it is exposed to the atmosphere, we have nothing is there, only the conductor and insulation is there. Then what will happen? It will expose to the surface on the ambient, wherever it is laid, either it is laid in air or it is laid in underground. So this, all the ambient pollution will come in contact with the insulation, and this insulation will get damaged with the time. So the voltage which you are considering zero over here, with the time that voltage will not be zero, there will be some voltage or there will be some damage of the insulation, then maybe full voltage will come on the surface. So we have to protect this insulation. So how we do the protect? We protect by putting some other cover over this, so that it will be protected from the ambient condition. Then problem will come in. So these are the three parts. One part is conductor, one part is insulation, some protection for the insulation that is also required. Now once this cable laid, then it may happen people will be walking over the cable, maybe traffic is going over the cable. So with that traffic movement, people movement, it may happen that this cable can get damaged with that pressure. So we have to protect the cable from that type of incident. So there will be another layer outside of this, which we call is armor, that is a mechanical protection, so that if some traffic goes over the cable, suppose in case the cable laid underground, so in that case if some traffic goes, the cable will not get damaged. Suppose the cable laid on the ear, some people walking over the cable, in that case cable should not get damaged. So there are some mechanical protection is also required, that is we call is armor, that is also required. Then fourth point is the entire system. When this armor also sometimes it may come in contact with the voltage due to earthfall or something, and then also this total system, if it is in a polluted area, suppose there is a fumes or some plant where is a petrochemical product is there, sometimes there will be some sulfur dioxide gas, suppose it is underground cable, but underground there are a lot of gases are there, all those gases can penetrate through this, and then that can damage this armor also. There is a possibility, because the armor is a metal. It could be aluminum, it could be galvanized steel, it could be stainless steel, it could be normal iron wires, it could be aluminum wire. So different material it could be, and this material with the time it can get damaged. To avoid the damage of these wires due to pollution, contamination, we need another plastic material cover, so that no gas, that is non-porous material, so that no gas or liquid can penetrate to this armor. So there will be another layer will be there. So these are the basic part of the cable required. So what are the basic part? One part is a conductor, that is the one part. Second part we need a insulation. Third part what is there? Third part we need protection for the insulation. Protection for the insulation. Fourth part what we need? We need for this mechanical protection. And then further we need to protect these mechanical items, we need another plastic covering. These are the basic part. Now in addition to this, there are some other things are required. What is that? This cable, that means from the conductor you can see, suppose this is I am drawing a length of the cable, suppose this is one length of the cable. Now with this length of the cable, so this is the conductor, over that there is a insulation, this is a insulation, right? Now that means this will be act as a capacitor. So this is a conductor and this is the insulation, so this is a capacitor. When the capacitor, it acts a capacitor, so there will be charge over here. So that charge, what can happen, this charge, and it will come in contact with the ear, then with this gap between these two will be ionized, and then there will be a ozone gas can be formed by the decomposition of the air, or this charge can cause a voltage on this surface, and that voltage is a dangerous for the cable or for this insulation. The insulation will get damaged. So what is the requirement? This charge to be drained to the ground. So what we do, over this conductor there is the insulation. Over the insulation, what we do, we put some either copper wire or aluminum wire or copper tape, and that copper tape will be grounded. So if any charge comes on the surface of the insulation through this conductor, the cable, the charge will be drained to zero, or no electricity will be on the surface. So this is called internal sheath wire or internal metallic wire. Over the insulation we can see this thing. This is called a metal tape to be provided to discharge this discharge this accumulation of charges, so that the outer surface will be always at zero potential. Okay, sometimes it is also due to, if there are three cable laid side by side, and if there is imbalance voltage, then the imbalance induced EMF will create a current in the outer sheet of the insulation. That current, the imbalance current should go to the ground, so that this metallic sheet also help to drain that current to the ground. That also is another purpose of the metal sheet. That means over the insulation there will be a metal sheet. In addition to this, there is another phenomena can take place. So that means after the insulation there will be a metallic sheath or metal wire to drain the charge or for the imbalance current due to imbalance voltage. In addition to this, another important point, there is electric stress in the cable. When the conductor, suppose a conductor is a high voltage cable, suppose it is a 33 kV cable. Suppose this is a 33 kV cable, this is a conductor, and over that we put the insulation. So now if this is the thickness of the insulation, then the 33 kV voltage will be diminished to 0 over here within a small distance. So there will be a high voltage gradient, kV per millimeter will be very high, and with the high gradient there will be a chance of failure of the insulation. That's why we don't allow that voltage gradient to be very high along the surface of the conductor or surface of the insulation. That's why what we do, this conductor we extrude with semiconducting tape or semiconducting material. Over the conductor there will be semiconducting material, then the insulation will be there. Over the insulation another semiconducting layer will be there. So the semiconductor, means it is between conductor and insulation. So the voltage gradient, suppose this is from the conductor to the insulation without the semiconductor, voltage gradients like this. Suppose there is a sharp voltage, this is a 0 voltage level and that is the maximum voltage. But if we put this insulation, then the voltage gradient will be gradually become 0. It will not be sharp 0. So that will give the privilege of chance, it will prevent the failure of the cable due to high voltage stress. So that's why we see when the conductor is there for the medium voltage high voltage cable, over the conductor there is a semiconducting insulation either in extrusion form or in the tape form, and over that insulation is there. Over the insulation there is another semiconducting layer. After that the metallic tape is coming. Okay, so these are the major component, but in addition to the, depending on the application, there some additional layer could be put in. Suppose the water cable is going through the water. If we want to dry cable, in that case over this insulation and the semiconducting material we put a water barrier tape, which will prevent penetration of water into the insulation. So there will be water barrier tape. And if we want to complete design of the dry, then we put a lead sheet over the cable, over this insulation semiconducting, then we put a water barrier tape, then we put over here lead sheet. After the lead sheet we go for the metallic tape, or the lead sheet can be used as a metallic tape, then we go for the further arrangement. So these are the basic construction of the cable. So in a brief, we can say cable has a conductor, and over the conductor for the medium and high voltage cable there is a semiconducting layer. Then insulation will come. Over the insulation there is a semiconducting layer. Over the semiconducting layer there may be water barrier tape. Over that it may be metallic. Then there will be metallic tape. It could be continuous metal tape, or it is a metal foil. It could be, or it could be metallic wire, long wire along the length of the cable. This can be put in. Over that should be wrapped with some polypropylene wires or polypropylene tape. Over the tape, that is the act as a bedding. Then we have to put the mechanical protection, that is mechanical armor. Over the armor, what we have to put? We have to put another plastic cover, that is a PVC, that is called outer sheet, which will prevent to inhale the cable any external liquid or external gas or anything, so that armor will not get damaged. So these are the major component of the cable. Now when we are going to decide the cable sizing, first part of the sizing is, what is the sizing? First part of the sizing, we have to decide what cross section of the conductor is required for carrying a particular amount of current. That is first part. So first part of from the system design point of view, if we want to carry a certain amount of power from one point to other point, the certain amount of power needed definite size of conductor. So we have first part, we have to decide that size of the conductor. So first part is the size of the conductor. Second part, what is that? We have put the insulation. Now there is a different voltage. So we have to decide which is the right voltage grade of the cable. So second part is the voltage level or voltage rating of the cable. That is to be decided. Okay. These are the two parts. Now when you go for the sizing of the cable, the sizing of the cable is only one of the part is there from the continuous. The sizing of the cable depend on the various parameters. Again, various subdivision. It has a separate subdivision. One part is a sizing cable to be sized based on the how much current or how much power it is carrying. That means we have to check the current carrying capacity. Continuous current carrying capacity. That is first part. Second part, we have to check with this continuous current, suppose a particular cross section carrying a current, certain amount of 100 ampere, suppose a 50 square millimeter cable, it is carrying 100 ampere current. Now when this 100 ampere current will go, and now for any length it can carry, or as a small length, that we know, because this current carrying capacity is depend, another parameter is involved here, we call the voltage regulation. Suppose there is a one point is here, from here we need to take the power, suppose 2 kilometer away here. So here is a certain, suppose it is a 6.6 kV voltage. So we need certain amount of voltage over here, suppose it is a 6.4 kV we need. So now this 2 kilometer cable or 1 kilometer cable is a conductor. It has a resistance, it has a inductance. So it will, there is a voltage drop along the cable. So if the same amount of power we carry for a longer and longer length, that may not be possible. So we have to check another point for a particular cross section. We decided based on the current, for that current whether that cable can carry the amount of power or that amount of current with a definite voltage drop. That also we have to check the voltage drop. We have to check whether we have the required regulation, voltage regulation is present or not. Suppose we need a 2% voltage regulation, means we will allow 2% voltage drop. So we have to see with the same amount of current going through the conductor is up to what length that will maintain 2% voltage. We can do up to that amount of length. If length is more than that, then that particular cross section area will not be suitable, because cable impedance is depend on the cable cross section area. We know the resistance is inversely proportional to the length. So if cross section area. So if we increase the cross section area, automatically resistance will be less. So for the same current, voltage drop will be less. So if that particular cross section area, it can take maybe 200 meter length, but if the length is 400 meter, then that cross section area is not suitable. So we have to check that current carrying cross section area, whether is it suitable from the voltage regulation point of view. That is the second calculation. Third point, if this cable carry a short circuit, suppose there is a fault on the cable. So in that, suppose there is a fault over here, the fault current will flowing through this. In that case, the cable should not burn out. So we have to see the same cross section area, because the cable short circuit current capacity, it depends on the cross section area. It is proportional to the cross section area. So if the cross section area more and more, it has a more and more short circuit current capacity. So this particular cross section area decided based on the current and voltage drop, whether that cross section area is suitable for carrying the whole current or not, short circuit current or not, that we need to check. So that is also another point. You have to take the short circuit current carrying capacity of this particular cross section area, which has been decided based on the current carrying capacity and voltage drop point of view. So if this three is met for a particular cross section area of the cable, then that cable is suitable for carrying that amount of power safely. That is the first part. For the sizing, in the sizing calculation, conductor sizing is then the conductor sizing is over. Now the second part will be what grade of voltage we have to use. For that, there is a voltage grade of the cable. So there are three different grades are available. We'll discuss this thing. That is for continuous voltage, and then we have a short time voltage rating of the cable as well, that we need to discuss. Okay. So these are that mainly two calculation is required to decide the cable sizing from the system point of view or from the design detail engineering point of view. So let's discuss the first part. First part is the conductor sizing of the cable. We have to size the conductor of the cable for a particular amount of power. For that, what we need to consider. So first part of this, to decide the current carrying capacity or conductor size of the cable, what we need to do, we have to first calculate the data, how much power we need to carry, then what is the type of cable is required, what is the cable, and then we need the cable manufacturer catalog, or we need to refer to the IEC. This cable sizing, all this thing is decided by IEC. The reference is IEC 606364. This is the IEC we are following for the cable sizing, and if we go for BS 761, we use for the cable sizing calculation. 364 is the IEC for the cable sizing. Okay. Now when you go for the first part, cross section sizing of the cable for cross section area. Now this cross section area for a particular amount of current, when you want to carry, first how we calculate the current, we are first deciding the continuous current rating based on that. Now for that, this cable is connected between the source and the load point. So each load has a kilowatt or kVA. From that kilowatt and kVA, if we know the voltage of the cable or voltage of the system, we can calculate the current. We have already decided, we have already seen how the current, we know this. Suppose kilowatt, we know the kilowatt, then kilowatt equal to for 3 phase, how much? 3 phase root 3 into voltage into current into cos phi power factor. So kilowatt, we know the kilowatt, we know the voltage of the system, we know the power factor of the system, then we can calculate the current from here. Kilowatt by root 3 into voltage into cos phi. Cos phi is the power. Suppose there is a motor. We have a 100 kilowatt motor operating at 6.6 kV voltage. So immediately from this formula we can calculate the how much current it is delivering. Now this current, this is the output. This kilowatt is the output, right? This is suppose this is a switch gear. There is a breaker and there is a motor is connected over here. We have to keep in mind to calculate this current. This is the motor. Now this kilowatt, what is mentioned over here, this is the output of the motor. Always we mention kilowatt, we mention on the motor, that is the output power. This motor can give this amount of kilowatt to the pump or fan. This is the output. So now motor has some loss, it has some efficiency. So if you calculate it, because cable is connected to the input side or here, so we have to calculate the input power before how much power input to the motor. The motor is giving this kilowatt, because on the nameplate, whatever the kilowatt mentioned in the motor nameplate, that is the output power. So that means the power coming from the motor. So how much power coming on the motor? That is, we have to divide by efficiency of the motor as well. So here to get the full load current. So here will be efficiency factor will come also in case of motor. Okay. So by this way we can calculate the incoming cable full load current. This is the full load current we can decide. Based on the full load current, now we have to decide what is the cross section area of the cable is required. So we can immediately to discuss what type of conductor we are using, either aluminium or copper. So for aluminium or either aluminium or for copper, now there is a IEC, what the say IEC 364, there is a table for the current carrying capacity, the copper conductor, aluminium conductor for each section. So from that we can find out for this particular amount of current I, what is the cross section area is required. Now here there is a problem. Now here is the issue that this cable, when you go for this table or chart, either manufacturer table or the IEC table, then you can see there is a current capacity of a particular cable is different under different installation condition. Now how many installation condition over there? From the installation point of view, this cable can be installed on ear. Suppose in the overhead we install overhead tray, that can be possible, that is in the ear. It can be put on a trench. Ear, suppose there is a ground, over the ground we put a trench, open trench. So this is open, it is ear, fill up with ear. So there is a trench over here. Suppose this is a cable trench, over the cable is there. In that case also this cable laid on ear. So this is a ear laying cable. This cable can be laid under the ground direct. Suppose there is a ground, this is the surface level and this is a ground. Okay, we can put the cable over here and it will go like this. So in that case the capacity is different. So here this could be provided underground and it is directly buried. This cable is directly buried. Another, we can lay the cable, we can make underground some duct bank. Duct bank is a big pipe we can install, and inside the pipe we can put the cable. We can also lay the cable in this way. So underground, one we can put directly underground, directly buried underground. Another we can put underground, but it is under duct bank. We call it duct bank. Generally oil field we use this arrangement. Duct bank in Saudi Aramco, you can see a lot of duct bank. And here also all the American installation, you can see there is a underground, there is a big trench is there, inside there is a duct bank, and every distance there is a manhole through which you can get the access. So this way also you can lay the cable. This is the arrangement. Then the cable can be laid in water also. It could be underwater cable also. It could be possibly like a submarine cable, or it is a complex underground cable. The cable can be laid in underwater also. That is also possible. It is also possible the cable is laid in various mediums. Suppose a long length of cable is going, some portion is going through here, some portion is going through underground, some portion going through underwater. All this arrangement is there. That is also possible. So in the various condition, except the last condition, forget this condition. In all other condition, whether it is laid in here or laid in underground directly buried, or laid in underground under duct bank or underwater, the cable rating, current rating for suppose there is a 50 square millimeter cable. This 50 square millimeter cable, if the cable laid in here, it has one current rating. If you go for underground, it has another current rating. If you go duct bank, it has another current rating. So the manufacturer or the IEC has a separate table for each size of the cable, how much current it can carry. It is in the ear, then it can decide how much current. If you go for underground, it can decide how much underground current is carried. So you have to refer to the respective table for which you are planning to install this cable. Suppose you are planning to lay the cable in here, then you have to consult the table which is showing the current carrying capacity of a cable or various size of cable in here. So from that you can say I have the requirement of the current. This is my current requirement. From that we will get some cross section area A from the table. From the suppose the cable laid in here, so we will refer to the table which is meant for the ear laying cable. So from that we get to get this amount of current we need this square millimeter of cable, size of cable. So this is we get from the table. Now this table, all the as per IEC, the current carrying capacity of the cable is decided on the ambient temperature, and that ambient temperature is considered 30 degrees centigrade. Okay, this is as per the table we get this cross section area. Now this cross section area is not the final. Why not final? This current carrying capacity of the cable is dependent in case of ear. First we are considering in case of ear laying cable. In case of ear laying cable, this cross section area is dependent on other two parameters. One is what is the ambient temperature, the ear temperature where the cable is laying, because in IEC the cable ear temperature considered 30 degrees centigrade, ambient temperature 30 degrees centigrade. Accordingly the cable has been prepared. If you go to the manufacturer, some manufacturers this cable designed for 20 degrees centigrade. Some manufacturers they design their cable for 40 degrees centigrade. So different manufacturers have a different ambient condition, or they may go as per IEC 30 degrees centigrade. So from the table when you get a particular cross section area, you have to search in the table for what temperature, what ambient temperature that cross section area is mentioned. If my actual installed condition is not the same ambient temperature, then I have to correct it. So there is a correction factor we call it a uprating or derating factor. Suppose the cable laid at 30 degrees, the design table is for 30 degrees centigrade. Now I am putting a cable in a cold country, temperature is 20 degrees centigrade. So automatically the same cross section area cable can carry more current, because as the ambient temperature go up and up, immediately current carrying capacity generally get fall. And current carrying capacity, it is not only depend on the conductor, it depend on the insulation also. For every 5 degree dropping of temperature, current carrying capacity will increase by about, for the XLP cable about 4 to 6%, and in case of PVC cable about 6 to 7%. So this temperature also important parameter. So in IEC or in the manufacturer catalog, we get this derating factor table. There is a temperature and corresponding derating. Suppose 30 degrees centigrade, the derating factor is 1. Then if you go 35 degree, you may say it is maybe 0.96. If you go 40 degrees centigrade, it may be 0.92 for XLP cable, like that. If you go 25 degree, it may be 1.04, like this. So this type of one table is there. From the table you have to calculate, suppose we call this is a temperature derating factor KT. So from this table, either IEC table, if you go for IEC rating, or if you go for the manufacturer, then the manufacturer cable table we have to consult, and then we have to calculate that temperature, ambient temperature derating factor from the table. So that will be one of the factor, that is called KT. Okay, we can get from the table. Now, so this capacity of current which we get from the table, that is at 30 degrees centigrade as per IEC. So if we go for 40 degrees centigrade, then it will be 92% of that. That means this will be multiplied by 0.92, or otherwise you can say this will be multiplied by KT. That will be the current carrying capacity of this cross section area cable at 40 degrees centigrade. Now there is another factor we call as grouping factor. Now when we lay the cable in the ear, suppose the cable laid in a tray, suppose this is a tray. On the tray only one cable could be there, right? So then this will be the rating. But if there is a multiple cable, suppose the cable touching each other, in this way you laid it. In that case, each cable when is carrying current is producing heat, and then there will be electromagnetic flux also this producing all around. So all the cable will be interference with each other temperature as well as that electromagnetic flux. So in that case, what will happen? The cable current capacity will be reduced. So this is another factor we can see in the table, that is we call grouping factor. Cable grouping factor. The how many cables you are laying on a particular layer, what is the distance? Maybe another way you can put on the tray the cable. Cable is not touching each other. There is a gap between the cable by 1 dia. Suppose this is the diameter of the cable 1D. So there is no cable over here. There is another cable after 1D. Then there is a gap. There is another cable on the 1D. If you lay the cable in this way, then there will be different grouping factor. So for each arrangement in the manufacturer catalog or IC catalog, we can see the group factor of the cable. What is the group factor? So we can calculate the group factor, we call it kg. So that means depending on the laying arrangement, we get this group factor, and we have already got another factor called KT. temperature derating factor. So if we multiply these two, we get the overall derating factor, that is called K for the ear-led cable. So that will give you the this A area, this cross section area fixed. This cross section area carry I amount current. This I amount current with the temperature derating. If I multiply I into KT, then that will give the at T degree centigrade what is the current carrying capacity. When you multiply this by group factor, then it will give this current, this amount for this cross section area, how much current this cross section area, the cross section area cable can carry at T degree centigrade with this grouping condition, will get by I into K, this way. So this I into K amount of current will be carried by A cable, A size cable. Suppose this is 100 ampere and this cross section area was 70 square millimeter. Okay. Now at normal condition 30 degree centigrade with a single cable, it will carry 100 ampere current carried by 70 square millimeter cable. But when you go for 40 degree centigrade with a 3 cable laying, we get this group factor, it may be 0.9. So then what will happen? It will carry not 100 ampere, then same cross section area cable will carry 90 ampere current. So our current carrying capacity will be 90 ampere. So that means now if we have a 100 ampere current, then we have to increase the cross section area. Suppose my full load current 100 ampere, based on that I see the cable is a square millimeter. Now the same A square millimeter cable, when I apply the derating factor, it is carrying 90 ampere current, but my current is 100 ampere, so I cannot use A ampere current. Then I have to go back to the table and we have to see that 100 ampere current, we get the 90 ampere current for this condition. So if we want to get 100 ampere current, then what is the factor? That will be 100 ampere divided by K, that will give the current rating. Then this amount of current I have to size the corresponding cross section area. Is it clear? So actual cable which can carry this 100 ampere current, that cable current will be I by K. That will be suppose I2. Then we have to calculate this from the table. To carry this I2 current, what is the cross section area is required? That may be cross section area A1. That means this 100 ampere or I amount of current to carry at the ambient temperature of T at the group factor of K, we need A1 cross section area of the cable, which is equal to how much? That is equal to this current, rated current divided by K group factor. From that we will get that current, and from the table for that current we have to calculate the cross section area. In this way we can calculate the cross section area of the cable from the current point of view. Once it is decided, then next part we have to go for the voltage drop calculation. We have set three. One is the cross section area we decide. Next part we have to calculate the voltage drop of the cable. How we calculate the voltage drop? We know the voltage drop is there is a formula for the voltage drop. The voltage drop formula for a cable VD, that equals to for three phase, root 3 into I into L into R cos theta plus X sin theta, where R is the resistance for the, if this is the length L, this is the per unit length resistance and this is per unit reactance, and theta is the power factor of the load or the current, you can say. How we will get this thing? Actually this is suppose this is a sending end voltage and this is the voltage Vs, and there is a power factor, suppose this is the current I, power factor is theta. So in that case this will be IR, okay, and then perpendicular to this will be IS. Suppose this is a IX voltage drop, though this will be your receiving end voltage. So this will be the drop, this is your VD. Now this VD, now this will be your VE, that is your sending end voltage. This is your receiving end voltage. VR is the receiving end voltage, this amount is the receiving end voltage, this is the drop. If we add vectorally, this will be VS. So how much drop? This is the voltage drop. So this voltage drop we can calculate in approximate way. If we plot an arc over here, then this will be the radius of this. So the voltage drop, this amount we can approximate this amount. So this will be actually two part. One part is this A and another part is B. And this angle is theta, means this angle is theta. So if you calculate A and B, it will come R cos theta plus X sin theta. And that multiply with the full load current and then the length, then it will get the three phase voltage drop. This is the approximate formula. But if you calculate the complete formula, like this, if you calculate this VD, not the approximate, this amount, then this will be more tedious formula will come. We know the current of the cable, how much current is carrying, we know that is the current I, and we have already size of the conductor. Conductor size, already we got the conductor size A1, and from the cable manufacturer table we can calculate the R and X per unit length, per meter or per foot as per the table. How much resistance, how much reactance. We know the power factor of the load. Suppose with the motor power factor is already on the nameplate. We have considered the power factor in calculation of the full load current. So this factor we know. From this we can calculate the voltage drop. Once we get the voltage drop, then we can check whether the voltage drop is acceptable to us or not. As per NEC, they said that voltage drop from the main source for IEC 63, IEC 60364 or BS 761, you can see from the main board up to this. Suppose this is the main source reference point. From there is going to another switchboard, and from the switchboard it is connected to the load. Suppose this is the motor. So as per NEC, from the main source up to the end point or the reference voltage point to the end point, maximum voltage drop is allowed 5%. So out of that we consider the main voltage drop is 2%, branch circuit voltage drop is 3%. That is the guideline to check the voltage drop in the normal operating condition for continuous full load current. From the main reference voltage, main source voltage where the transformer is connected. Suppose this is the transformer is connected, so this is the reference voltage. From this board up to the load point or the furthest mode point, total voltage drop under normal continuous operating condition is 5%. So if this out of this 5%, main board voltage drop will be 2%, branch circuit voltage drop is 3%. So now from this point, suppose we are now calculating the cable size for this. So in that case, how much voltage drop allowed? 3%. We can calculate the voltage drop. If this voltage drop is within 3%, then this voltage drop is acceptable. If this is not there, then what we have to do? What is in our hand? In our hand, this length is not in our hand. Length is constant because this is a point where the switch gear, the motor is connected over here or load is connected over here. So this length is a fixed. I cannot change the length. So this is not in our hand. What is in our hand? Only the R and X, because R is the resistance per unit length resistance. Per unit length resistance depend on what? On the cross section area of the cable. That means now I have to, if the voltage drop is less, then it is fine. But if the voltage drop is more than 3%, then I have to reduce the R and X. R, how I can reduce? We know resistance of a conductor is inversely proportional to the cross section area. That means if I increase the cross section area, then resistance will reduce. So we have already select the cross section area based on the full load current. Now the full load current is fixed, we cannot change it. Now we have to increase the cross section area to get the required voltage drop. So what about the cross section area we consider? We'll go to the next higher size cross section area. Suppose before it gets 70 square millimeter. Now we'll go for 90 square millimeter cable. We calculate the resistance and inductance, then we calculate the voltage drop, whether the voltage drop is coming within 3% or not. If not, then we'll go further down, maybe 100 square millimeter cable. We'll go like this way. We'll have to gradually increase the cross section area till we are not achieving less than 3% voltage drop for the branch circuit or less than 2% voltage drop for the main circuit. This way voltage drop to be calculated, and this is the approximate formula. In case of single phase, it is for 3-phase circuit. In case of single phase circuit, what will happen? This length is the main board to the from the source point to the load point. But in case of single phase circuit, what will happen? This cable will go and come back. So this is neutral cable. So this will be 2 times. So instead of √3 for single phase circuit, it will be 2 into IL for single phase circuit. Okay. And for the DC circuit, what will happen in the DC circuit? There is no angle. There is no sin theta. Theta is 0. In the case of DC circuit, what is the theta is 0? So that means theta 0 and sin theta 0, cos theta 1. So this will be R only. So this will be how much? I into L into R. But DC circuit same like AC single phase circuit, it will return circuit, so it will be 2LR. So from this equation, this is a common equation which you can apply for the AC circuit, DC circuit, single phase circuit, 3-phase circuit, all the circuit. In case of single phase circuit, it will be multiplied by 2. In case of 3-phase circuit, it will be multiplied by √3. In case of DC circuit, this will be 0, it will be multiplied by 2. So in all cases, we can use this formula for calculating the voltage drop. Once these two are decided, then we have got the final cross section area of the cable. Now we have to calculate the short circuit resistance capacity of the cable with that cross section. Now you see, after this cable current carrying capacity and the voltage drop capacity, suppose we get the cross section, final cross section area A0. Now the short circuit current of the cable withstand capacity, that equal to some factor K into A by root of T. This is the formula. T is the time. If you consider for time T equal to 1 second, then the short circuit current capacity will be K into A. A is the cross section area, suppose in this case A0. Now K is a factor. That factor is actually, if we consider when the fault takes place, the amount of heat produced in the cable that is limited within the cable, we call it the adiabatic type of expansion or adiabatic condition. In that condition, the K factor is depend on the what type of insulation you are using and what temperature difference you are using. You know, this cable, continuous current rating of the cable is estimated based on this temperature of the conductor. In case of copper conductor, PVC insulated copper conductor, this temperature we call 70 degrees centigrade continuous. And in case of XLP insulation copper cable, we call it a 90 degrees centigrade. Okay. So there are two grades. One is a 90 degrees centigrade for the XLP insulated cable, and copper insulated cable, PVC insulated cable is a maximum temperature is 70 degrees centigrade. That is for continuous normal operation for the cable. But when there is a short circuit in the cable, then this corresponding temperature for PVC, it goes to either 140 degree or 170 degree. There are two grades, 140 degree or 170 degree. And XLP cable from 90 degree centigrade, it goes to 250 degree centigrade. XLP cable short circuit condition, under short circuit condition, the temperature withstand capacity is very high. It is a 250 degree centigrade. So depending on the temperature, suppose you are using XLP cable, XLP copper cable, operating initially 90 degree centigrade, and when short circuit takes place, it will go up to 250 degree centigrade. In that case, the K value will be 143. K value will be 143. Okay. So in that case, current will become as 143 into A0, 143 into A0 by root T. For 1 second, it will be, this will be the current carrying capacity of this ampere. A is in a square millimeter. This will be in a square millimeter. Okay. So this will be, suppose it's a 100 square millimeter cable. In that case, how much? 143 into 100 means 14.3 kiloampere will be 1 second fault short circuit withstand capacity for 100 square millimeter cable if it is XLP cable. But if you go for this PVC cable, then this 143 K factor will not be 143. K factor will be approximately, it will be 90. Instead of 100, it become 90 K factor. And if you go for 90 degrees centigrade, suppose initial temperature is 70 degrees centigrade, and you go rise of 140 degree, not one, it is this 90 will get in case of 170, then it will become 80 degrees centigrade. 80, the factor will become 80. So you can, this table, this value you can get in the IEC, respective IEC, and you can calculate this value. Okay. So these are the short circuit current. So we have to see now, suppose I have a short circuit current of 20 kiloampere for 1 second. And if I go by the XLP cable for this, I am getting 14.3 kiloampere. So it is not meeting the requirement. In that case, what I have to do? I have to increase the cross section area of the cable. Now, first we increase the cross section area for the voltage drop. Now again I have to calculate I have to increase the voltage drop A0. Now new A0 will be how much? It is a 20 kiloampere divided by 143. So from here we can calculate 20 kiloampere means 20,000. We can calculate the new cross section area of the cable. So this way cross section area in every stage will be corrected till the short circuit current withstand capacity is checked. So by calculating the continuous current capacity, voltage drop capacity and the short circuit current capacity, ultimately we are getting the final short circuit current, final cross section area of the cable, which is suppose A0. So this is the cross section area of the cable is required for carrying this current from one point to other point with maintaining the voltage drop profile, maintaining the short circuit current withstand capacity and this current rating. But whatever the size comes, generally we put another one size higher from that point, considering future if some additional load requirement is there or not. That is for the continuous current rating. But in case of motor cable, when we decide the motor cable, we have to calculate the continuous current rating of the cable from the voltage drop point of view, as well as we have to calculate the starting with that cross section area. We have to check the starting voltage drop. One additional voltage drop calculation is required. That is a motor starting voltage drop calculation, because as per IEC we say that motor should start at 80% voltage. When the motor terminal voltage is 80%, That means 20% voltage drop we are allowing from the switchboard after the motor during starting time, because starting time motor current is above approximately 6 times in case of DOL starting. So with the 6 times current, we have to check whether the motor during starting cable voltage drop is within the 20% or not. If it is less than 20%, that cross section is very fine. If not, then we have to increase the cross section area again in case of motor cable. But normally we do not consider 20%. What we do during motor starting, we keep 5% cushion in our hand. So we allow 15% voltage drop. Now 15% out of 15% voltage drop from the main board to here, it is a, instead of 2%, we can go up to 5%, and balance 10% we drop in from the point here to up to the motor circuit. We allow up to 10%. This way total 15% we allow, but if it is not become very high, in that case we may limit here 3% and we can go here 12%. So this way 15% voltage drop we maintain in the case of motor starting. Okay, this is the voltage drop calculation point of view. So sizing is finalized. So this is the cable sizing calculation, cross section area sizing. Next part that we have to select the proper voltage rating of the cable. Now the cable voltage drop is decided, continuous voltage rating of the cable is decided based on the grounding condition of the system. Now based on the grounding condition of the system, there are 3 category of voltage. One voltage category we call 100% voltage cable, another we call 133% voltage cable, and one is 173% voltage grade. What is this? This 100% grade cable means this cable where it is connected, that system, suppose this is a transformer, from the transformer this is a switchboard, and from the switchboard cable is connected. If this transformer neutral is solidly earth, suppose this is a star connected, a star is solidly earth, okay, this is a delta, this side is a star is solidly earth, and this voltage is going to the switchboard. So this is the switchboard, from here the cable is going. It may happen like this. If this is the arrangement, it is called solidly earth system. In case of solidly earth system, we use 100% rating cable. That is that cable, the cable which is used for the solidly earth system, that cable we call 100% rated cable, and that cable, if there is a fault, the fault will be clear within 1 minute. Within 1 minute the fault will be clear. Second is a 133% cable. In that cable, the cable is not solidly earth, it is a low resistance earth. That means the start point of the neutral is connected with a resistance, low resistance. So this is called low resistance earth. In case of low resistance earth, we use 133% cable, and if in that case if there is a fault will be clear in 1 hour. In 1 hour time the cable fault will be clear. That is called, and in that case we use 133% voltage rating cable, and 173% voltage rating cable you use when the neutral is not grounded at all. It is an unearthed system, or it is a resonance acting. It is a neutral is not grounded, or it is grounded through the resonance grounding. In that case we use 173% voltage rating cable, and in that case the ground fault will not be cleared. It is a unlimited time is required to clear the ground fault. Okay, so this type of system we use 173% of voltage rating cable. What does it mean? 100% voltage rating cable means, suppose system voltage is 6.6 kV, that means there is a 6.6 kV face to face voltage. Okay, now that means how much phase voltage? Phase voltage by root 3. 6.6 kV by root 3 means how much? It is a 3.8 kV, right? So that means this 100% voltage cable means the cable will be 3.8 kV. You know, the voltage rating of the cable as per IEC, it is designated by this way. Okay, the voltage rating of the cable as per IEC, then it will be more clear how we define voltage rating of the cable as per IEC. We designate it as U0 by U within bracket UM. This is a U0 means it is a phase to ground voltage, phase to earth voltage. U0 is a phase to phase voltage, voltage between the phase to phase voltage, that is a line voltage, and this is the maximum voltage. Like suppose it is a 3.3 kV system. 3.3 kV phase voltage how much? 3.3 kV by root 3. Suppose in a 3.3 kV system, how this voltage is mentioned in the IC, if you see, if you go for 3.3 kV system, the phase voltage is 3.3 kV by root 3. The 3.3 kV root 3 is 1.9. This divided by 33, 3.3, and within bracket this is 3.6. That means this is the maximum voltage. So this cable we call the 100% cable. So if we have a solidly earth system, where the 100% rated voltage cable is required. In that case, we identify the cable will be 1.9 kV by 3.3 kV within bracket 3.6 kV. This cable is called 100% voltage rating cable. So for that system, we have to identify, this cable is required. But if the system is low resistance grounded, in that case, as per IEC, we will not use this cable. What will use? We will use 1.9 into 1.33. That will be your U0. And U will be how much? 3.3 into 1.33. And UM will be 3.6 kV into 1.33. That will be the new voltage rating of the cable. And if the cable we use this same 3.3 kV system, it is unearthed system. In that case, this factor will be 1.73. 1.73. What does it mean? It is actually root 3. That means 1.9 into root 3. That means it's become 3.3 kV. That means the cable, now the cable will be not 3.3 kV, it will be 3.3 kV by, it will be 6 kV. If you multiply 3.3 into 1.732, it is about 5.9 kV, it is 6 kV. And that 1.33 means about 8 kV. Maximum voltage will be 8 kV. That will be the voltage grade of the cable. Okay. In case of insulated system, that is a 173% cable. So in this way, cable voltage will be decided. The continuous rating of the cable voltage will be decided based on the grounding condition of the system. Okay. For 100% system means as per this, if the solidly ground, you will go for 100% rated voltage cable. If it is a resistance or grounded system, you have to go 33% voltage rating cable. In case of unearthed system, you have to go 173% cable. Means in that case, the 3.3 kV, which is the phase voltage 1.9 kV, the phase voltage you have to consider 3.3 kV. That means you have to go for 6.6 kV cable for 3.3 kV. That is the impact of this. This way we can decide the continuous voltage rating of the cable. The next part is the short time voltage rating of the cable. Now, in case of short time voltage rating of the cable, what we do, as per IEC, it is there. The short time voltage rating of the cable, it could be, if you go, this short time voltage rating of the cable is specified in terms of 1 minute, in terms of 15 minutes, in terms of 30 minutes. And how you are doing the test of the cable. If you go the over voltage rating calculation check of the cable through DC voltage, then that voltage will be for 15 minutes. Okay, 15 minutes. But if you go the over voltage capacity of the cable to be checked by AC voltage, then it will be for 1 minute. And there is another very low frequency. If you go for the very low frequency voltage test, then that with a shunt capacity in terms of 30 minutes. Suppose this is a 3.3 kV system, 6.6 kV, 11 kV, 33 kV, 66 kV, suppose up to 62 we are considering. In case of DC voltage, which is for 15 minutes, if you go for DC voltage, in that case, the cable voltage will be, it is for 15 minutes. 15 minutes, 3.3 kV voltage will be 7 kV, it is a 15 kV, it is a 25 kV, it is a 50 kV, and it is a 75 kV. That will be the DC voltage required if you want to check the DC over voltage capacity of the cable. But if you decide that I will check the cable with respect to the AC voltage, then the AC over voltage capacity for 1 minute, it will be how much? It will be considering for 3.3 kV system, it is 10 kV, it is a 20 kV, it is a 28 kV, it is a 50 kV, and this is a 70 kV. But if you go for, if you plan that I will test the cable by very low frequency test, then this you have to identify, then you have to tell that for it will be test for 30 minutes with a stand capacity, and in that case, that will be how much? That will be 6 kV for the 3.3 kV, it will be 12 kV, it is a 19 kV, it is a 38 kV, and it is a 57 kV. That is for 30 minutes. This will be the over voltage capacity of the cable. In that way, we will decide the over voltage capacity of the cable. So these are the three things we need to decide, or we need to determine when we are going for cable selection. Now, in addition to this, we have to another point is important point. This is we are considering either it is cable laid in air, or cable laid in underground, or cable laid in water separately. But if the laying route contain all three, then what we will do? Suppose from this source point of view, the cable is laid, part 1, suppose it is in air, then part 2, that is in water, and part 3, it may be underground. If the cable is laid in this way, then for each area, we have to calculate the cross-section area. what is the cross section area, because here only the important part voltage drop is not very important, but we have to calculate this area, what is the current carrying capacity required. Suppose here current carrying capacity required A1, when the cable laid in here, considering the full load current, what is the current required, and the voltage drop, we need A1 cross section area. Here we will calculate, suppose we get the cross section area A2 to meet the water requirement. When you come to underground, then we get suppose A3. This is the 3 parameter we got. If we get this 3 cross section area, now we have to see out of this 3 which is the highest cross section area. That highest cross section area, suppose this is the highest this is the highest. So in that case, we have to take the highest cross section area of the cable for the entire route. But if any of the route is very small, suppose this is a 0.35 meter, it is 1 feet, in that case that is need not to consider. This way we have to calculate the cross section of, in case of multiple media, we have to calculate the each area, what is the cross section area required, out of this what is the highest cross section area, that to be considered. So when we are going for this way, we have already discussed in here how to calculate the cross section area, but in case of underground cable which we are frequently leading, that part we have not discussed. Now if we go for the underground area cross section area, we will decide in the same way. We will calculate first the full load current, how much, root 3, that is we have calculated how much this will be. Full load current I equal to kilowatt by root 3, this is a kilowatt by root 3 into voltage into cos phi into efficiency, we will get the full load current. Now for that particular full load current from the table, we can find certain cross section area, suppose A. Now we have to check this cross section area is suitable for considering all the ambient condition. In case of cable laid in here, we have only 2 factors, temperature derating factor, ambient temperature derating factor, and group derating factor. But in case of cable laid in directly ground, there are 4 good derating factor. What is a, suppose the cable laid in underground, this is the ground, cable laid over here, it is filled up with soil, there is a, here is a ambient temperature, here will be soil temperature. So there is one factor, that is KT, that is for the soil temperature. Second factor is, same like a group factor, here is also there is a group factor, how the cable is underground, it is in touch or it is get separated, so there is a group factor. The third factor is at what depth the cable is laid under the soil. That is another important parameter. So that depth, there is another factor KD, that is a depth factor, that is another factor. And the fourth factor is the soil resistivity. Soil resistivity has impact on the cable current carrying capacity. So the soil resistivity has one factor, that is called K, soil resistivity, KS you can say. So all the 4 parameters, there is a table in the ISC or the corresponding manufacturer catalog. From that catalog we have to calculate these 4 factors. Normally in case of directly buried cable, KT is normally 1 for 20 degrees centigrade soil temperature. If the soil temperature is different from 20 degree, suppose it is for every 5 degrees centigrade, in case of XLP cable, same like here temperature, it derated by about 4 to 6%. And in case of PVC cable, it is about 6 to 8% or 6 to 7%. Similarly, group factor as same like our ER cable. Now this third is a depth factor, generally 0.8 meter depth. In that case, the depth factor is 1. If the depth is more than 0.8 meter, then the group factor is operated. This depth factor is operated. But if the depth is less than 0.8 meter, then it is a derated. So that way the derating factor is decided for the depth, and this resistivity factor, derating factor, generally if the value is the 3, then this value is 1. But if the value is more than less than 3, then generally as the resistivity low and low, it is more conductive. So the derating factor will be changed, will be increasing. In case of more K value more than 3, it will be derated. So this derating factor also we can get in the table. So these are the 4 derating factor. Once this 4 derating factor is decided, then out of this 3 derating factor, we can calculate the final derating factor K equal to KT into Kg into K resistivity, soil resistivity into K depth. This 4 derating factor we multiply, we get the final derating factor. Once we get the final derating factor, then whatever the current we got, that current divided by derating factor will be the final cable current. Suppose it is I0. For that I0, what is the cross section area required? That we will find out from the table. That will be our A0. That A0 we will consider for the further voltage drop calculation and all other calculation. This way we can calculate the voltage sizing of the cable, right? So this is all about the cable sizing and cable, how we decide the cable, and that is all about. But one thing I want to highlight, when there is various software available to calculate the cable automatically, but you have to make sure that voltage drop they are using the right formula, not the simple formula, and all other parameter, all the constant has been considered based on the if it is in the design stage, then you use the IEC parameters. But if it is after procurement of the cable, if you go for the final check of the cable, in that case you should use the respective manufacturer catalog, not the IEC, because manufacturer design may be different at the temperature, all the factor may be different, so you will get different factors. So at what stage you are deciding the cable? If the cable already in your hand and you want to you want to install the cable, then you will use the cable catalog. But if the cable initially before ordering you are deciding this cable, then you use IEC. Or if you have a plan 3-4 contractor, then you should tell them that they should calculate all this thing accordingly. They should come back to you. Okay. So this way we can estimate the cable. That is all about cable sizing. Cable sizing for the our daily requirement. Now next session we will discuss about the cable testing. We will not discuss over here. Next section we will go for the UPS, AC/DC UPS sizing. How we will do the UPS sizing, that part we will discuss in the next session. Thank you very much for joining in this discussion and kindly keep it up. Thank you very much.